Problem number 4. Theta in each of these problems represents an angle, and we want to state in which quadrant the angle lands without using the calculator. The reason we can do that is that the inverse trig functions only know about a few angles. For example, in part A, the inverse sine function, the 0.7 is a ratio being stuck into the inverse sine function. Inverse sine only knows about angles between negative pi over 2 and positive pi over 2. In other words, in quadrants 1 or 4, well, sine ratios are negative in quadrant 4, so if I have a positive ratio, I must then be in quadrant 1. Letter B, tangent inverse negative 5. Tangent inverse has the same restrictions as sine inverse. It also only knows about quadrants 1 and 4, negative pi over 2 to pi over 2. Well, this time I have a negative ratio. I know that all the ratios are positive in the first quadrant, so I must be down there in quadrant 4. Letter C, cosine inverse is the only one that works differently of the big three. Cosine inverse knows angles between 0 and pi. Well, again, I have a negative ratio. I couldn't possibly be in quadrant 1, so I must then be over here in quadrant 2. And then be careful with letter D. Maybe it's tempting to say quadrant 1 again here, but a sine ratio equal to 2, some quick thought thinking about the unit circle or the graph of the trig function should make you realize that's not possible. There is no such thing as a sine ratio of 2, and so this is undefined. You'll never have a sine ratio larger than 1 or smaller than negative 1. In problem 5, we want to give some approximate answers to those angles we were talking about in number 4. And so we'll just have to go to the calculator. We do want degrees, it says. So I will need to put myself into degree mode first. And then it's just a matter of typing them all in. The first one is sine inverse of 0.7. We wanted it to 1 decimal place, so that's 44.4 degrees. And then we've got tangent inverse of negative 5. And so we'll put that in the calculator, and looks like negative 78.7 degrees. And then cosine inverse of negative 4/7. And when we put that in the calculator, we've got 124.8 degrees. Letter D, of course, was undefined. Problem number 6 is a review on finding equations of sinusoidal graphs. It says we want to find the simplest equation, meaning don't use a phase shift. If we don't want to use a phase shift, I should start here at the y-axis and kind of trace along until I identify one of my familiar shapes. And of course, when I do that here, I see that I have the hill and the valley, which is regular sine. Another thing that might help me to do is to draw in the midline. The top is 3, the bottom is negative 1. Halfway between those two numbers would be positive 1. You can always add them up and divide by 2. And I think I have enough on here now that I can identify some of my pieces. My A value would just be the amplitude. A distance from 1 to 3 would be 2, positive 2 because of the regular sign. My B value, let's see, what's the period? That would be where the hill and valley ends. It ends here at 2 pi. Well, I have the little formula B equals 2 pi divided by the period. In other words, the period is just the normal period. The B is just 1. There is no phase shift because we set it up that way. And the midline we've already determined is at positive 1. So if I put all those pieces together, the equation I'm going to get is y equals 2 sine x, I don't have a b or a c, plus 1. Okay, let's try the second one. So starting at the y-axis, of course, when I trace out my familiar shape, what I see is the ghost. And with the ghost, we know that that's reflected cosine. Let's see, the top is 4 and the bottom is negative 4, so that just means the midline is at 0, halfway in between those two numbers. My A value, let's see, the amplitude is obviously 4, so A would be negative 4 because of the reflection. Let's see, is the B just 1 again? Where does the thing end? Here's the end of the period. It's right at 2. So we are going to get a different value. B would be 2 pi divided by the 2, which comes out to be pi. So B is pi. We have no phase shift, and we have no midline change on this one either. So it looks like the final equation here, y equals -4 cosine of pi x. And again, no d at the end. In problem number 7, we're looking for a value of x. X represents an angle in these expressions. We're doing this by hand, giving the smallest exact radian answer we can find. Of course, when we see numbers like ones and negative ones and zeros with sine and cosine, we're thinking unit circle pictures. Let's see, part A says, I'm looking for an angle where the sine comes out to be -1. Now on the unit circle, the sine is the B coordinate of any point. So where would I have something comma -1? I believe the only spot would be down here at 0, -1. Well, I want the smallest positive angle that would lead me there. That's going to be this angle right here, which is 270 degrees, or in radians, 3 pi over 2. Letter B, similarly with cosine. Cosine is the A coordinate. This is the only spot on the unit circle with an A coordinate of -1. So this time we're looking for this angle, which of course is 180 degrees, or pi radians. Now, letter C, tangent x is undefined. On the unit circle, tangent is given by the B coordinate divided by the A coordinate. The only way this could come out undefined is if the bottom part is 0. So I'm really looking for spots where the A part is 0, 0 comma something. Well, I think that happens twice. Once here, 0 comma 1, and once down here at 0 comma -1. But I'm just trying to give the smallest positive angle that would work. Well, that's going to be hitting this first spot here by rotating 90 degrees, or in radians, pi over 2.